The distributive property of exponentials. When you think about the distributive property, you maybe think about how it relates to the Fourier method, or maybe how it relates to the base of every higher order exponentials, or maybe how it relates to a quadratic formula and the Pascal's triangle, even the binomial theorem. And now they could look a lot of different ways and usually have some really intrinsic properties of roots, slopes, derivatives, local maximum and minimums, inflection points, absolute maximum and minimums. The predicament properties of the distributive property. I said we have a goal of x plus 1 squared. Now what this goal is basically saying is what is an initial number with 1 added to it then squared. Now we can see from this that this isn't a one-step process, it's a two-step process. And so the distributive property is modeling that two-step process, but it's doing so mathematically. We can use this chart right here to illustrate this. That the initial values will simply just be the first step, and the extra values will simply just be the slope. One contradiction comes to mind when we think about this, that the final result will simply just be just x squared plus 1 squared, but that's just not true. That's only the first stage of the equation. We can't find an increase of a number simply by squaring it. We need another stage for this. Stage 2. This extra stage illustrates a function of the second distributive phase of the distributive property, essentially adding the function of an extra value of its slope or derivative. And so when there is a will, there is a way. And so the stage 2, the terms multiply each other. Stage 2, modeling the increase of x squared. Now, stage 2 represents the second phase of the distributive properties, and it is associated with the slopes of an equation. So basically, a long time ago, mathematicians figured out how exponential numbers proportionally increase based off its factors, a times a. So now we can derive this hypothetical theory of distributive phases for exponentials, saying if you have a square number x squared, you're able to create a process and find an x squared by adding x proportionally to the sides. And we can derive the slope prototype and the additive slope prototype from this. We can illustrate this with x squared and then x squared with the prototypes of x and x. We can see how it proportionally fits a square and creates another square proportionally to x squared. And so we have a breakdown of it, a more concise breakdown. The slope of x squared to x is on the sides of the factors, and that the additive slope is covered by the factors of the slope. Higher order illustrations. We can see here this x plus 1 squared predicament ratio of x to x correctly models the slope of x squared of simply 2 or 2x. Now this predicament ratio is the base of all x n power exponentials. It models their slope through au times a, as n multiplication terms conclude to n minus 1x times x. Now we can see an example here of x to the fifth power, simply illustrated as x to the fourth power times x. And so that is how the derivative exponent rule is derived. Scaled up ratios of exponentials. Let's take a look at some scaled up ratios of exponentials. Let's take a look at x squared plus 2x plus 1. We'll see how this square represents all that it needs to get to the next square number. It has the slope and the additive slope. We can also see the same thing also with x to the third power plus 3x squared plus 3x plus 1. We'll see how it has a slope and the additive slopes to get to the next x plus 1 number. We can also see a comparison here between this number and x plus 1 squared, that they basically compare each other almost proportionally. And that those slopes compare each other, and that the slope is always the second value in the equation. We'll see the same thing here with this equation, with x plus 1 squared, that the slope is always the second value in the equation. Let's take a look at how the different quotient rule utilizes the phases of the distributive property. The different quotient rule strategically utilizes the phases of the distributive property, creating differentiation with subtraction and division to isolate the derivative. We can see this here by x plus h as a function being subtracted away from simply just x as a function. We'll see how the x squared, which is the initial value, subtracts, and we are left only with the slopes and basically the derivatives. And now we divide by h, which factors away the h's from the slope derivative. And now we are left with the derivative unaffected by the h. And now the additive slope is only the one that's affected. And now we're able to limit the h to 0 to be left with only the slope of the equation. And that's how the different quotient rule works.